There are so many biological questions we don't have answers to. And if there is one constant in the world, it's the evolution and development of technology. I kind of look at the genomic tool set developing in your standard 1.0, 2.0, and 3.0 step. 1.0 allowed us to identify the letters in the alphabet. 2.0 allowed us to identify every letter in the book. Where we see spatial applications is truly the 3.0 step. You're looking at the book because the story is right in front of you. The story is the disease that's presented in the tissue or cells in their natural state. And story matters. One of the most daunting questions right now in biology is how can two people with a similar disease have completely different outcomes? So, for example, two women that present with cancer, a very common approach now is to have your tumor profiled. When you extract the nucleic acids, that step by itself removes context because you don't see where those gene expression patterns exist within the tumor. So one of the attributes of molecular cartography is we preserve tissue integrity because context matters. This is the Google Maps approach. So you can start at the country level and move down to the state, the city, the neighborhood, and eventually the individual house level, right? And so spatial technologies allow us to do the same thing where we can look wide view at a large piece of tissue and to be able to see all of the interactions that are happening. Where I think it's quite interesting is as you collect enough ground truths, you start to see patterns that emerge in the data. And this is where biology has a long way to go. But if we can create large enough data sets, we can see patterns in the signal. And those patterns in the signal are those ground truths within the biological map. So let me give you a very real scenario as to why location matters. My grandmother did pass away from Alzheimer's disease. For those who have been through an Alzheimer's situation with a family member, you know how devastating it is. The brain is a complex organ. And as you can see in our images of the mouse brain, you can see very distinct bands of colors. And those colors are specific genes to specific cell types. We can modulate the genes differently, and we can identify, for example, genes that are expressed with beta amyloid. And so we've done studies looking at how certain gene expression patterns vary as a distance from the plaque. And we believe that by identifying genes that are involved in the growth of the plaque, we're going to be able to identify targets and potentially stop the progression of the disease. My message to the scientist is we understand the struggle, and we understand the fact that current technologies aren't answering the questions that you need answers to, so that those two women both survive cancer, so that your grandmother doesn't pass from Alzheimer's disease. We get it, and we are committed to creating the next generation of tools that helps you focus on what matters.